So in the last video about comparators, we've learned that we can create multi-bit digital comparators that can compare two multi-bit inputs and tell us if they are equal to each other. And of course, we learned that we can just do that using an exclusive NOR gate, also known as the is equal logic gate. But of course, there's other functions that that a comparator can do as well. Of course, you can not only just test for equality, but you can also test to see if A is greater than B, and you can also test to see if A is less than B. These functions, of course, are very useful, just as useful, I would argue, as testing for equality, but the implementation of these functions are a little bit more complicated, which is why I wanted to save them for their own video. But I figured now was probably a good time to explore the inner workings of this function, so I figured I'd make a video for you to show you how all of that works. So before we dive into multi-bit inputs, of course, let's just take a look at single-bit comparators here. So suppose I have two single bits coming in, going into a box like this, and I wanted to produce three signals coming out. One that told me that A was equal to B, the other that said A was greater than B, and the third that said A was less than B. How would we do that? Well, once again, let's take a look at the truth table. So of course we have A and B, and then we have our three outputs. We'll call it Q equal, Q greater than, and Q less than. So A and B, of course, are going to have, they're either going to be on or off, so we can list every combination of inputs like this. So it's 0, 1, or 0, 0, 0, 1, 1, 0, and 1, 1. So that's every combination of A and B. Now, testing for equality is fairly easy. You just want to see when A is equal to B, of course. So if A is 0, B is 0, and if A is 1, B is 1. So that's going to be these two conditions right here. In these two conditions, of course, A and B are not equal, so there's 0. This is the truth table for an exclusive NOR, as we've established in the last video. Testing for greater than, however, in a binary system with 0 and 1, there's only one digit that's greater than the other. So if you were to look at 1, no digit is greater than 1. But if you were to look at 0, there's only one digit that's greater than it. So if we want A to be greater than, or if we want A to be greater than B, we need A to be a 1 and we need B to be a 0. So A is 1, B is 0. In this instance, A is greater than B. And in all other instances, A is not greater than B because, of course, in these two instances they're equal, so they can't be greater. And in this instance, A is a 0 and B is a 1. Well, 0 is definitely not greater than 1, so that can't be true. So this is the only instance where A is greater than B. And likewise with less than, we just saw that this is the only instance where A is less than B. A is a 0 and B is a 1, so we put a 1 there. All other instances, they are not less than. So this is the truth table for greater than and less than, and that translates into a logic gate fairly easily. If I were to make a logic gate that checks for greater than, for example, we're looking for A as a 1 and B as a 0. That AND is the key word there, of course. So if we run it through an AND gate like this and we invert B, this AND gate is only ever going to be on when A is 1 and B is 0. So this tests for a greater than condition. And if I were to do the same thing, but in reverse, so invert A and leave B as it is, this tests for less than conditions because it's looking for B when it's a 1 and A when it's a 0. So what about multiple bit inputs, of course? We learned in the last comparator video that we can create multiple bit inputs by just ANDing all of the single bit inputs together through an AND gate. So for example, if we were to compare each of these bit by bit, these are equal, so the result of that comparison would be a 1. Likewise with these bits, and these bits, and then ANDing all of them together would result in a 1. So this result would tell us that these two inputs are equal. So you might think that we'd be able to get away with doing the same thing with our greater than and less than comparison logic gates. But that's actually not the case. If we were to do something like an ANDing here, we could see, of course, that In this case, A is definitely greater than B, and our logic gate would test for that, so that would result in a 1. But in all other instances, there's 0. And so if we were to actually AND all of that together, because we have zeros in this result, the output is going to be 0. So this is telling us that this number, A, is not greater than B. But very clearly it is. I mean, if you were to translate these back into decimal, this is 8 and this is 7. 8 is greater than 7. This should be a 1, but it's not. So you might think that, okay, well, we'll do something like an OR kind of situation. Well, if we were to look at something like this, we can see that, well, A is less than B, so that's going to be a 0. A is greater than B, so that's going to be a 1. And likewise with these, they're 0. So ORing all of these together, we get a 1, which this is telling us that A is greater than B. But if you were to translate this into decimal, this is a 4 and this is 11. 4 is less than 11, so this is wrong too. So we need to establish some sort of algorithm that allows us to detect when one number is greater than or less than another, and obviously simply just using single bit comparators and performing some sort of logical operation between them all isn't going to cut it. So if I were to ask you to compare these two numbers and tell me which one was greater than the other, you could very quickly tell me that A was greater than B, and the reason why is, well, it's intuitive. A is clearly larger than B, but intuition doesn't translate into a circuit very well. What we need to do is we need to break down the individual steps taken automatically by our brains that tell us if A is greater than B or not. And so the way we actually do that is, if you actually stop and slow down and pay attention to how you check, you always check with the highest order digit first, or the most significant bit. And you check there, and you look to see which one is greater than the other. In this case, A has a 1 and B has a 0, so A is greater than B. And once we know that, we actually don't care about the rest of the bits. We can ignore them. We've already established that A is greater than B, so the answer here is, in fact, A is greater than B. But what if we have leading bits? Say something like this, where both sets of bits are equal. So the only difference, of course, is in this set of bits right here and this set of bits right here. All other sets of bits are equal to each other. Well, again, we would still start with the greatest or the most significant bit here. So we'd of course compare those, and we would look to see which one was greater than the other. In this case, they're equal. So you might make the assumption that these are of course equal, but of course sending both these numbers through a digital comparator testing for equality would show immediately that no, these are not equal. So it's not equal, but these are showing equal. So what we say at that point is, we don't know. So then we move on to the next set of bits. We look there and we see that they're equal again, but again, digital comparator tells us it's not equal, so we don't know. So then we move on to the next set of bits. And we find that they're equal again, so we don't know. Next set of bits, they're equal, so we don't know. And it isn't until we get to this set of bits here that we look and we find that they're not equal. And that's the key. We're starting with the most significant bits, and we're working our way down to the least significant bits until we find the first set of bits that are not equal. And in this case, whichever one has the 1 is the one that's greater than the other. So A has the 1, so in this case, A is greater than B. Now suppose I had a 1 over here. Well, if performing the same algorithm again, we would actually stop at this set of bits right here, and immediately at that point tell that A was actually less than B. So as soon as we come across a set of inequality bits, we can look at which one has the 1 and tell that that one is either less than or greater than the other. And at that point, we don't care what the rest of the bits say. We already have our answer. So with this algorithm in mind, let's try and create a truth table that actually describes what the function of our circuit is. So again, we're trying to compare these groups of numbers together, starting with the most significant set of bits and ending with the least significant set of bits. And if we end up finding a less than or greater than condition in any of these bits in that particular order, we would be setting the less than or greater than flags over here. But if none of those conditions end up matching and we find that all of them are equal, we would set the equal flag. And so that last one is actually fairly easy. We've already established this. So if we say that A3 is equal to B3 and A2 is equal to B2, A1 equal to B1, and A0 equal to B0, then we would say that the result is equal, and it is not greater than, and it is not less than. But the other conditions are a little bit more tricky. So how do we go about that? So again, like I said, starting from the most significant set of bits, we would test for equality or not equality, or in this case, less than or greater than. And again, we would have our three logic gates that would do that. The exclusive NOR, which is going to test for equality, that's going to tell us this. We have the AND gate with the B inverted, that's going to tell us our greater than condition. And we have the AND gate with the A inverted, that's going to tell us our less than condition. So we would look at this first set of bits and we would test to see if they were greater than or less than. So if A3 was greater than B3, again, because we've determined a greater than condition at the most significant set of bits, we don't care what the rest of the bits say. And at that point, we've immediately determined that A3 is greater than, or A is greater than B, so we would put a 1 in the greater than flag, and all other conditions are 0. Likewise, if we find that A3 is less than B3, we again don't care what the rest of the bits say, and we know that A is less than B. So a 1 in the less than flag and a 0 everywhere else. So what if neither of these conditions are true? Well, if that's the case, we would move on to the next set of bits. We would check to see if A2 is greater than B2 or less than B2. But we don't want to be testing this arbitrarily. Obviously, if we're testing A2 and B2, we don't want to say that we don't care about these, because we don't care about these necessarily. If we find that A2 is greater than or less than B2, we don't care what A1 and B1 and A0 and B0 say. So we can say we don't care about those too. But what we do care about is A3 and B3. We can't just say that we don't care, because if A3 is greater than B3, well, this condition should in fact be set, in which case we wouldn't even bother with this. Likewise, if it was less than, we wouldn't bother with this. So we do care about A3 and B3. In fact, we want to ensure that those are equal. Because if these are equal, only then do we want to look at the next set of bits. So if A3 and B3 are equal, and A2 is greater than B2, again, we can determine that the greater than flag is on, all other conditions are off. Likewise, if A3 is equal to B3 and A2 is less than B2, we can determine that it's a less than condition, all other bits are off. Now, the same principle applies for the next set of bits, of course. I'm just going to speed through these, but effectively, again, we're going to test for A1 and B1, making sure that one is greater than or less than the other. And once we determine that, we actually don't care what A0 and B0 say. Oh, wrong symbol. We don't care what A0 and B0 say, so we can ignore them. But we don't want to be testing these arbitrarily. We only want to test them if A3 is equal to B3 and A2 is equal to B2. So we write equals in all of these points, and likewise, if A1 is greater than B1, it's greater than. If it's less than, it's less than. All other conditions are 0. And likewise with A0 and B0, we're testing for greater than or less than only if all of the others are equal. And when that's the case, greater than when greater than, less than when less than, 0 in all other instances. And this actually covers all of our bases. So we start with the most significant bits, like we said, and we test for inequality, and we go with the result that matches whichever one has the 1 in it. So if A has the 1, we're greater than. If B has the 1, we're less than. And if they're equal, well, then we go and move on to the rest of the truth table, testing for A2. Likewise, if those are equal, we move on to the rest of the truth table, testing A1 and B1. If they're equal, we move on, and A0 and B0, we test for those. And that's basically our final say if the number A is greater than the number B. And if that ends up failing, obviously at that point we can safely assume that they're all equal and the equal flag is set. So now let's look at translating this truth table into a circuit. So here we have sort of a modified equality comparator circuit here. We can see we've got the exclusive NORs connected to all pairs of inputs, and they all go to an AND gate. And that AND gate's result, of course, tells us if A is equal to B. But we also have, in addition to that, our less than and greater than comparators tied to each set of bits as well. So using our our truth table, let's create a logic gate that can produce the greater than and less than results too. So the first one, of course, is easy. We can see that greater than is going to be 1 if A3 is greater than B3. Well, here's A3 is greater than B3. So we can just tie that directly to the greater than output. Likewise with less than, if A is less than B, which is this AND gate here, then it's going to produce a less than result. So we'll go ahead and tie that like that. So that's probably the easiest part of this whole thing. So the next one, of course, is going to be the same thing. It's going to be A2 and B2 is greater than or less than signals passed over to these OR gates, but only if A3 and B3 are equal. Well, this logic gate right here, this exclusive OR, or exclusive NOR, tells us that A3 and B3 are equal. So what we can do is we can say that we're only going to consider these gates right here if this is a 1. And we can just do that with an AND gate. Or rather, 2 AND gates. So one is going to go through one, the other is going to go through the other, and these are only going to be enabled when this exclusive NOR shows that A3 and B3 are equal. And then, of course, we can just pass that right up to the OR gates, and I'm probably going to run out of room here. I'm going to try and keep this as tight as possible. Just like that. So now, just like our truth table shows, A2 and B2 are only going to be compared for less than or greater than conditions if A3 and B3 are equal. Likewise with A1 and B1, we're going to create some AND gates. We're going to pass that through. But this time, A1 and B1 are only being considered if A3 and B3 are equal and A2 and B2 are equal. So we're actually taking both of these exclusive NORs into consideration. And that's actually not that difficult. We're just going to tie those to the AND gate as well. So now, these outputs will only be on if A1 is greater than or less than B1, and A3 is equal to B3, and A2 is equal to B2. And likewise, we can just route these right up to their appropriate logic gates. And lastly, of course, we just have A0 and B0, and that's more of the same. Again, these outputs are only ever going to be on if the 3 previous sets of bits are compared and found to be equal. Now, this is a little bit of a mess, I know. There's a lot of spaghetti wiring happening up here. But this is effectively the logic circuit that's going to implement the truth table that we've derived from our function. And so this, with a little bit more reduction and simplification, is our digital comparator circuit. Now again, there's some things that we can do to simplify the circuit greatly. In fact, if we perform these simplifications, we can get a circuit that looks like this, and this is actually the schematics for an actual manufactured digital comparator that tests for equality, greater than, and less than. And so one of the simplifications that we can do, of course, is we can combine these logic gates together. Because of course this is going to be an AND gate that's comparing between A and not B, and it's going through the equal of the previous one. So we can actually take these logic gates, we can smash them together, and just route these exclusive NORs through directly to these logic gates, which is exactly what we're doing right here. We can see that we've got these AND gates that are connected to their respective A and B inputs, and they're also connected to the exclusive NOR gates. In fact, this one is connected to all 3 of the previous exclusive NOR gates. However, you may notice that there's actually a lot fewer AND gates than there ought to be. Here we've got, for a 4-bit input comparator, we got 2, 4, 6, 8 AND gates, and here they've only got 4. What happened to the other 4? And the answer is they got rid of it entirely because it's actually not necessary. You'll notice that we have the standard circuits for A equals B, we have the exclusive NORs, and we have the AND gate, and we have the circuits required for A greater than B, which is those AND gates connected to everything else through the OR gate, which is what we've got right here. But A less than B is actually just a NOR gate between the two. Why did they do that? The reason why they did that is actually, if you look at this truth table here, you'll notice that at all instances, one of the three outputs is always on. We're always going to have a greater than, or less than, or an equals signal. At least one of these signals is always going to be on. And what's more is, at most, one of these signals is always going to be on, because anytime a greater than signal is on, you're never going to get an equal or less than signal. Likewise, with less than, you're never going to get equal or greater. And when it's equal, of course, you're definitely not going to be getting less than or greater than. You can see there's only one condition where that's true, and the other two outputs are off. So if really all you really need is just two of those outputs, and you can derive the third. Because if one of them is always going to be on, and the other two outputs are off, then it must mean that the third is on. And so if you look back at what they've done, that's exactly what they've done. What they've got is a NOR gate, which is a not OR. So in other words, if A is equal is on, or A is greater than is on, then this output is going to be on, but of course it's inverted, so it's going to be off. So in other words, if either one of these is on, this less than output is going to be off. If both of these, however, is off, then we know for a fact that A is less than B, and this output automatically turns on. It's just a little shortcut that saves you a few logic gates. Now in this case, for something like this, it doesn't actually save you all that many. It only saves you 4 AND gates and an OR gate. Actually, not really, just 4 AND gates. But for something much larger, if you're sitting with an 8-bit comparator, or 16-bit, or 32-bit comparator, this can save you quite a lot of logic gates. And so something like this is a little bit of a shortcut, and of course, fewer logic gates means smaller and faster circuits. So if you ever build a digital comparator, you don't actually have to build it like this. You can do this shortcut where you only test for equality and greater than, and then just derive the less than through a NOR gate. And of course, you can also do the opposite. Of course, you can have an equal, and you can have the less than comparator and derive the greater than through a NOR gate. It works just the same. But this is just a little shortcut that engineers use to reduce the number of logic gates, and it works just the same.